Right, today we're talking about Chapter 6, Section 4, and if you thought 6.3 was short, 6.4, well, there's fewer examples anyways. We'll see if it's shorter. We're talking about adding and subtracting radicals. So, the main thing we want to talk about is the definition of like radical. So what is the definition of a like radical? Alrighty, so the definition of a like radical is two radical, was it is or are? Are, no it's is. I don't know. The definition of like radicals. Two radical terms are called like radicals if they have the same index and same radicand. Okay, so they must have, notice here, same index. Same index in both cases is that implied 2, right, square root. And same radicand, the number inside the radical, and both of them have x. That is the definition of a like radical. You have to have the same of both. All right, so this is add or subtract as indicated. So whenever you're adding or subtracting like radicals, you can just kind of think of them as just variables essentially, right? They're not, but let's assume that a was 6x minus 2x, right? Well, 6x minus 2x is 4x, right? Well, assume that the x is the square root of 11. Okay, so we would have 6 on the square root of 11 minus 2 on the square root of 11, and that's equal to 4 on the square root of 11, right? Because we have the same indices, right? They're both an implied 2. We have the same radicand. They're both 11. So we can do this easily, add or subtract like radicals. Well, we have the square root of 3 plus the square root of 3. Well, the square root of 3 is the same thing as the square root of 3, and there's 2 of them. So we just say is 2 on the square root of 3. Easy peasy. Nope, this one's pretty easy too. Again, you can just treat them like radicals. Not radical, man, you can treat them like variables. So let's just go ahead and treat these like a variable real quick. Let's look at a real fast. A is negative 2. Well, let's just look. Do we have a like radical? We have, they're all the cube root. Perfect. What's going on here? Okay. We have a cube root, and they are, the radicand in each of them are the square root of AB. Or, I'm sorry, the cube root of AB. So all we have to do is just basically add or subtract the constants out front. So we have a negative 2 plus a 7, so negative 2 plus 7 is 5. 5 minus 1 is 4. So my solution here is just going to simply be a 4 on the cube root of AB. And then B. In both cases, we have the square root of 3y, perfect. And of course, we have the variable x in front, so all we have to do is do 1/4 x minus 3 halves. Well, 1/4 minus 3 halves is going to be equal to 1/4 minus 3 halves, 5. So it's going to be a negative 5 halves x on the square root of 3y. Okay, so those two examples are pretty darn easy because we had like radicals, and like I said, all we do with like radicals is just kind of treat them like variables. Well, these next two examples are not as easy. Instead, what we have to do is turn them into like radicals. Okay, so a is 3 on the square root of 8 plus the square root of 2. Right? You can't just look at this and say, well, they're not like radicals, move on. No, we have to change them. We have to turn them into like radicals. So what we did in the previous section, when we reduced the radical, we have to do now. Okay, so we can rewrite a as, so it's 3 on the square root of 8. So let's just do some scratch math down here. We have the square root, and we need to have a square of 2 in there, right? Well, 2 squared times 2 is 8, right? Because 2 squared is 4. 4 times 2 is 8. And I could take the square root of 2 out, and it would just be 2 on the square root of 2. Okay, so that's what we're going to do with A. And of course, this 2 right here is going to be multiplied by the 3 right here. So it's going to turn into 3, not 3, sorry. It's going to turn into 6 on the square root of 2 plus the square root of 2. Well, 6 plus 1 is just going to be equal to 7 on the square root of 2. B. Let's see. We have the we need to get a like radical, so keep that in mind. So in order to get a like radical, we need to have, it looks like in both cases, they need to have just the square root of x cubed in there. Which is actually kind of funny because it kind of violates one of the rules we talked about in the first section, or in the previous section, but that's the textbook, right? So we can rewrite the first one, right? We have, again, just do some napkin math here, just looking at x cubed y squared. I know that I could take the square root of y squared out, so I can have, so it would be y on the square root of x cubed. Okay, so I can change this into a, believe, yeah, we can do that. So we can change this into, no, no, let's just follow the rules from the previous section. I was going to keep the x cubed in there, but we're not going to, because I want to follow the rules of the section, and hopefully the textbook did too. So here we go. Again, napkin math here. We're going to have 8 on the square root of, and we can change this x cubed into x squared times x, right? We can change it into x squared times x, and then times y squared, and then minus 3y on the square root of, same thing, x squared times x. So I chose those specifically because the square root of x squared, I can take that out, I can take this out, and I can take this out. So I can rewrite this as 8x y on the square root of x minus 3, and then the square root of x squared, again, is x y on the square root of x. So I can rewrite it like so. And then now I have a common radical, right? So we have, again, the indices are the same. They're both the square root of x. The radicands are the same. They're both x. And from previous sections, we can only add or subtract like variables, and they're both x, y. So we are doing pretty good here. So 8xy minus 3xy, well, that's just going to be 5xy on the square root of x. And then C, oh my goodness, C looks horrible. Okay, so C, um, let's actually give C its own page. Let's do that. That way I'm not scrambling and trying to squish solutions into small little pockets there. All right, so we've got the square root of 50x squared y to the fifth. So let's just go ahead and rewrite this entire thing, and we're looking for perfect squares because it is a square root, right? So we're going to have the square root of, well, I know 25 times 5 is a perfect square, so 25 times 5, and then times x squared. X squared can remain there, times, we're going to say y to the fourth times, I really want to fix that for, there we go, times y. Yeah, close enough. And I'm going to go ahead and underline my perfect squares, because that's what I like to do sometimes when it's when problems get a tad complicated. I think this qualifies. Then 2x squared, and we're going to underline the x squared. And we're just going to do y squared y. underline the y squared. Hopefully I'm not running out of room here. And then plus xy, and then the square root of, and I know 98 is 49 times 2, and I know 49 is a perfect square, and then times y squared y. Okay, so it all barely fit. It looks like a mess. My shoulder's hurting, but we're doing it. Oh, okay, so this is not 5 times 25, it's 2 times 25. Sorry about that. All right, so now I can try to clean this up. Okay, so I can pull out what's underlined in yellow in the first term, so I can pull out a 5. The square root of 25 is 5. The square root of x squared is x. And the square root of y to the fourth is y squared. What remains is the square root of 2y minus, and then we have 13, and we'll just keep the 13 there for a moment. It looks like we have the square root of x squared is x, and the square root of y squared is y, but we have a y already there to begin with, so y times y is y squared. And what remains is 2y, and then plus, we can pull out the 7 there, square root of 49 is 7, and then the x remains, so let's just put that in yellow, and then the square root of y squared is y, and then y times y is, again, y squared, and all that on the square root of 2y. Whew, okay, so we've got the same, we have like radicals, we also have like variables, so all we have to do is simply just add or subtract this now. So we end up with a 5 minus 13 is a negative 8, negative 8 plus 7 is a negative 1, so we're going to have a negative xy squared on the square root of 2y. 2y. All right, so that was an adventure. Lots of computation there. And then, well, the last one. We're not going to risk it. We're definitely going to do the problem because we've seen where the textbook just kind of likes to not complete their work sometimes, I guess. Okay, so add the radicals. Assume that x is greater than or equal to 0. Alrighty, so we can reduce this. So let's just do this like we have been doing. So we have a 3 on the, and it's again the square root of 2, and then we're going to change. Well, let's just put x squared, and we'll underline that in yellow. Plus the square root of 8 can be reduced into 2 squared times 2. Of course, we've seen that plenty of times before now. And I'm curious why this one is the last problem, because this one seems fairly easy. Oh well. All right, so we can rewrite this as 3, and then the square root of x squared is x on the square root of 2 plus, well, 2, which we can do this as 2. Oh, I see what it is now. So the square root of 2x, I'm sorry, the square root of 2 squared is 2, and then what's right, the square root of 2. So this is why it is the last problem. We can't just simply add or subtract this because yes, we have like radicals, true, but we don't have the like variables, right? One of them has x, one of them does not. So instead, what we're gonna have to do is we're gonna have to factor. Right? If we look at this problem, what do we have in common? And let's actually make it a different color to really show it. So we've got the square root of 2, square root of 2. Okay, so obviously the square root of 2 is in both of them, right? So what I'm going to do is I'm going to factor the square root of 2 out, and what remains is a 3x plus 2. And that's that. That's pretty good. I like that. All right, so maybe publishers are onto something here. Anyways, that does conclude today's lecture.